Hello team. In this we're going to discuss control loops, which is one of the core concepts into the managers and controllers that we have for cloud computing. In the control loop, we have a desired state that we give a controller, and the controller will take adjustment actions on a process so that the process reaches the desired state. So we have this monitoring module that reads the current state of the process, sends it to the controller, and then the controller takes some adjustment action, the process adjusts, and then we measure the current state compared to the desired state. And while the process doesn't reach the desired state, the controller will keep taking adjustment actions so that the process goes towards the desired state. And this loop over here, reading the current state, comparing it to the desired state, and taking an adjustment action is the control loop. So let's have a look at some examples to make this more concrete. So here we have a control loop for cruise control. The desired state is the target speed. So we give the target speed to the cruise control, say 60 kilometers per hour, and then the cruise control will read the car's current speed from the speedometer and might brake the car or accelerate the car so that it reaches the target speed. So the control loop will keep reading the current speed, comparing it to the target speed, and then adjusting the car's speed by braking or accelerating so that we keep in the desired state. And this control loop will run indefinitely until we brake the car or accelerate the car. And then it will leave cruise control and we're going to control the car manually. Another example is heating in homes. Air conditioning system will read the current temperature from the thermometer, compare it with the thermostat, and then accordingly heat, cool, or just remain off depending on what the current temperature is. And in cloud computing, we can have many different controllers for many different desired states. For example, we might want to control the target CPU utilization on our microservice. So we give the target CPU utilization to the autoscaler, and then the autoscaler will monitor our microservices. There's going to be this resource monitor. It's going to read the current CPU utilization on our microservice, and it's going to be, for example, the average current CPU utilization. And if the current CPU utilization is above the target CPU utilization, we're going to scale out and create more instances of our microservice. And if the current CPU utilization is below the target CPU utilization, then we have more instances than we need. We're going to scale in and remove some of the microservice instances. And if the current CPU utilization is close enough to the target CPU utilization, then the autoscaler will not take any action, and we're just going to leave the microservice running as is. So a control loop is a declarative interface. We say what the desired state is, not how to achieve it. And the controller takes care of reaching the desired state. In the cruise control example, when the car is going faster than the target speed, we need to brake. But then the cruise control, the controller, can either brake smoothly, just a little bit, so that the car eventually reaches the target speed, or it can brake the car very strongly so that it reaches the target speed very fast. One important aspect in control loops is the control loop delay, or how frequently you're going to run the control loop. And there's no right or wrong answer. We need to look at the application and then decide on a loop delay that is reasonable for that application. In the heating example, it doesn't make sense to run the control loop very fast because heat takes some time to dissipate, and the temperature doesn't change very fast. So if we just keep measuring the temperature all the time to maybe adjust the heating or the cooling, it's just going to be wasting resources. For example, if we have a wireless thermometer, it might be burning out the battery on that thermometer and just wasting it because there's no need in measuring the temperature every 1 second, for example. And in cloud computing, again, we also have to decide how frequently the autoscaler loop should run. So if we run the autoscaler loop very fast, we're going to waste resources doing a lot of monitoring, and we might also issue a lot of requests before the system has had any time to react. If we run the control loop very slowly, then it might take too long to notice that the current CPU utilization has diverged from the target CPU utilization. So we need to pick a value that is reasonably frequent, but that doesn't overload the resources on the microservices and the machines. And just to give an example where we might want to run the control loop a little bit faster is in the case of anti-locking brakes. So in ABS, what we want the desired state is no skidding, so that the wheels are always turning. So we keep measuring whether the wheel is locked or not, or this is rotations per minute, and we send this data to the ABS, and then if the wheel is not locked, then we can brake, and if the wheel is locked, then we release the brakes a little bit just so the wheel begins running again. I guess the ABS does this like very fast so that it can keep traction all the time. So in the cloud computing example, the autoscaler might create new instances of a microservice. Then the microservices will take a few seconds to start. Then the load balancer will take some time to divert new requests to the newly started microservices. So there will be some delay between taking the decision of scale out and actual changes in CPU utilization. And this delay is what hysteresis is about. Another example is the heating. So when a AC starts to cool our homes, it takes some time until the temperature drops. And same thing with heating. If we turn the heat on, it takes some time until temperature increases. And control loops need to consider hysteresis to avoid undesirable conditions. So let's have a look at this example sequence of events. In time t1, the resource monitor tells the autoscaler that the microservice is overloaded. So the current CPU utilization is above the target CPU utilization. So the autoscaler might decide to scale out and create new instances. So let's say it creates 2 instances. So at time t3, so it takes some time for the new instances to start. Then at time t4, the load balancer starts to distribute load. So eventually, the CPU utilization of the microservices will decrease because now we have 2 instances and we're balancing load, but the utilization has not decreased yet because the load balancer just started its work. Then the resource monitor might tell the autoscaler again that the service is still overloaded because utilization has not dropped enough, just started dropping right now. Then the autoscaler might decide to scale out again because utilization is very high, and then it might create 2 additional instances. Now I might have 4 additional instances, and utilization will keep dropping because now I have additional instances and the load balancer is spreading requests across all of them. But 4 instances may be unnecessary. Maybe just the first 2 would be enough, and we should have just waited a little bit longer for CPU utilization to decrease. But here we didn't wait. We just notified the autoscaler that utilization was still high, and then it decided to create 2 additional instances, which might be too many. So we might waste some resources because we didn't wait for the CPU utilization to converge. So let's have a look at this in a more graphical way. So here we have time on the x-axis, and on the bottom here we have the CPU load. So red means that the CPU load is very high. And here on this line, we're going to be showing the number of instances of the microservice that are running. So here we have 2 instances of the microservice, and the load is very high. So the autoscaler will create 2 additional instances. We're going to have 4 instances. And after some time, the instances will come up, the load balancer will kick in, and load will start to decrease. This is orange area here because load is going down because now we have 4 instances. But at this point in time, the load hasn't decreased a lot yet. So the autoscaler might notice that the CPU load is still somewhat high and might decide to create 2 additional instances. Now we have 6 instances and the load will keep decreasing and it might become very low. After some time, the load will have converged and the CPU utilization will be very low. And in this blue area, the CPU utilization is below the target CPU utilization. So after some time, like here, the autoscaler will see that the CPU utilization is very low. So it might reduce the number of instances that we have. So it might, shut down 2 instances, and then we're going to, wait for those requests to finish and then shut down those microservices. And after some time, the CPU load will start to increase. But if the autoscaler checks the state of the system at this point in time, it will see that the utilization has increased a little bit, but not a lot, so not enough. So it might decide to remove 2 additional instances. So now I have 2 instances and the CPU load will keep increasing because now I have very few instances. And then after some time, the controller comes back up and now, oh no, the CPU load is very high. So now I need 2 more instances. Then it creates 2 more instances. And then after some time, the load starts to decrease, but it's still somewhat high. So it creates 2 additional instances. And then we keep getting this instability just because the autoscaler doesn't wait for the system state to converge. It just keeps, changing the number of instances without waiting for stability, and then we get this instability period. So keep changing the number of instances over time, and it's an undesirable state because the CPUs are underutilized or overutilized most of the time. The CPU they don't stay at the desired level, which is more or less at the middle of this orange area here. So we should avoid this instability, and this is one problem caused by hysteresis. So in this example, we're saying that we get instability because we are assuming that the workload is constant. So here, if we have, the same amount of users over time, and the number of instances and the load is fluctuating like this, then we have instability because it's constant workload, constant number of users, but this number of instances and the CPU utilization are unstable. But if we have actually a dynamic workload, then it's not instability and it's okay. So in this example, we have the amount of traffic going over an internet exchange point in Brazil. So you can think of this as the amount of people using the internet at any hour of the day. So this is, 6 a.m. when almost everyone is sleeping, and then people start to wake up, and then load increases, and then this might be like mid-morning or mid-afternoon, and there's, maybe end of the afternoon, beginning of the night, and then people go back to sleep. So this is this daily pattern of the number of users using a service, and most services that are regional have this, same trend of low load during late hours and high load during the day. And if our autoscaler increases the number of instances throughout the day and then decreases the number of instances during the evening, that's okay, because this is not instability, this is just the normal fluctuation of the system. So there's a difference between instability and load dynamics. So we should actually change the allocation while the workload is changing. That's okay. What we don't want is instability while the workload is constant. Another important aspect of control loops is action intensity. So whenever the control loop decides to take a decision, for example, the car is going down a slope and the cruise control is set at 60 kilometers per hour. So it will decide to brake the car. But it can brake the car in many different ways. It can brake the car super hard and then release the brake. So when it brakes super hard, the car decreases its speed, say it gets to 50 kilometers per hour. And then the cruise control sees that the car is going slower than desired. So it will release the brake and then the car will pick up some speed. Then after some time, the car will be at 70 kilometers per hour and the cruise control will kick in again and brake the car. But if it brakes super hard, then everyone will, feel this braking hard, and then the car will go down to 50 kilometers per hour and then to pick up some speed, and then the cruise control will brake the car very strongly again. So this would be uncomfortable because, we would get this like, a roller coaster. So it's not very, very nice. So what we might want to do in this case is to brake the car just slightly so that it keeps going at 60 kilometers per hour with no change in acceleration. And if the slope's more steep, then we want to brake a little bit harder so that again the car goes down at 60 kilometers per hour. And action intensity applies to cloud computing as well. So in the example I had before, when we were discussing instability in the autoscaler, I said that the autoscaler would scale out by 2 instances. But why 2 instances? Why not 1? Why not 3? Why not 4? So how many instances should we scale out each time? So this is one of the parameters that we need to set.